I think we can start this class. This is 16, because I gave you about 15 minutes so that a lot of you can connect as such. So we continue with sets and functions. We are continuing from sets and functions. So we looked at lecture number 1, we looked at lecture number 2. So now what we are looking at is lecture number 3 on sets and functions. So before we started with sets, then we came to relations and equivalent relations. Now we are looking at the last part of this topic, which is functions. Now, under this function, we are going to look at some basic definitions of functions and some of the properties involving functions. So we are going to look at some of the theorems that involve functions and also the basic definitions. Now, let's go to the definition of a function. So, so basically, in this part of the topic, we are going to discuss some basic ideas on functions and their properties. Now, the question is, what is a function? Before, if you look at, if you have a set A and a set B, let these sets be arbitrary non-empty sets. By being arbitrary, we are not defining, we are not restricting them. They can be set of integers, they can be real numbers, they can be complex numbers. So these sets can be any type of a set. It can be a set of rational numbers, can only be a set of irrational numbers. So now we are saying, let's have this set A and B, which are arbitrary non-empty. These sets should be non-empty. Then a function or mapping, we call it a function or mapping from a set A to a set B is a rule, is some rule which assigns to every member of A, or rather to every member X. This X is a member in set A, a unique member Y which is in B. So in short, what we are saying is, this function, we usually denote it by f, such that f which maps elements in set A to elements in set B. Now, the issue here is, this type of mapping is unique. What do we mean by being unique? So we are saying, this f, it acts on an element in set A, and the final resulting element in set Y is very unique, only one. So in short, every element in A has only one image. So it assigns to every element that is in set A unique determined member Y in set B. Now, this element which is in set B, the Y, this element Y, that you have found by acting this function on some element in A, which this same element, which corresponds in this way to a given element X which is in set A, is denoted by f of X. So we denote this by f, then open circle bracket, X, close circle bracket. This f of X is called the image of X under F, or f of X, we call it the value of the function at X, the value of the function f at the point X. Now, for this type of function, for the function f that maps the set A, that maps the elements of the set A onto the elements of the set B, this set A, you are getting elements in set A, then this function acts on it, it gives you elements in set B. So this set A, where you are picking those elements, we call it the domain of the function. In most cases in this topic, A will always be writing it as D subscript F, that means the domain of F. And the set of values of F which is the set B, is called the range or codomain. We call it the range or codomain of F. The range of this function, sometimes we write it as f of a, it is equal to, so the set, in short, B is equal to f of a. So the range of the function f is written as f of a, which is equal to f of x, an element in B such that x is in A. So this function contains all those values which are in B, all those values which are in B that you obtained by the function acting on those elements in A. So you obtain these elements in B by the means of the function acting on an element x which is in set A. So this is how we write in Z-build notation. This is how we write the range of a given function. Now, let's look at if we have two sets. This is definition 1 is continuing. So okay, maybe it's talking about the same thing. So it's a continuation. Now, if you look at the domain, let's try to take ourselves back. If you look at f of a, remember f of a has elements f of x which are found in B. So the range of this function is a set of all those values that you obtained by acting the function on the values in X. Now, this f of a, if you look at the way we have defined the domain of this function, this f of a is a subset of set B, is a subset of the set B. Now, if X is a subset of A, if X is a subset of A, then the image of this subset X, which is a subset of A, under F is the set f of X, which is equal to f of small x, which is an element of B such that X is in X. So now, in this scenario, this range has been obtained by acting the function on the elements of the subset of A. This is how we write it. Now, let's look at definition number 2. Definition number 2 is about the inverse of a function. So remember, what the function does, the inverse of the function decides to redo. You know, when you say redo, that means it takes back. So what we mean is it reverses the procedure. So if let f, which is running from set A to set B, be a function. Now, by being a function, we mean each element of A has a unique element in set B. Now, if y is an element of set B and there is an element x, if y is an element in set B and there is another element x which is in A, such that this y is equal to f of x. You know, what you're saying is, if you obtained this y which is in set B by applying this function on an element x which is in A, then x is called the inverse image or pre-image of y. This x is the inverse image of y or the pre-image of y. And in this case, we denote this x. If you want to write this x in terms of this function, we say x is equal to f inverse of y. So in short, if y is equal to f inverse of x, then x will be equal to f inverse of y. Now, again, if y, the capital Y, is a subset of a set B, then the inverse image or pre-image of this set Y, which is the subset of B, under F is the set which we write in this form in set below. So the inverse, the F inverse of this set Y is this type of a set, you are reversing the elements in B to be the elements in Y. So when this function f inverse acts on the elements of this set Y, the type of elements, remember, f inverse of Y is a subset of A, not of B. Y is a subset of B, but the f inverse of Y is a subset of A because it reverses the image to be, to be the element, the object. So the f inverse